So next talk is by Sabhapandit from the Raman Research Institute in Bangalore, and it will be about entropy production for partially observed systems.
Okay, yeah. So let me start by thanking the organizers, Shamik, Sourabh, and Arnab for inviting for this meeting, and also especially organize this meeting in the memory of Arun Jonever. Okay. So what I'm going to talk about is basically entropy production of a system, which is not a full system, but you just observe this entropy production for a part of a system. Okay. So as the talk suggests that as the name of the conference suggests that I don't need to give an introduction about this fluctuation theorem, and Rahul has already given a introduction, but just for the sake of this talk, whatever is directly relevant for this talk, I'll just give a very quick review of the fluctuation theorem, and then I'll jump into my part of the talk, which is basically the entropy production for a part of the system. So I'm going to pose this question and then mention a few earlier studies, and then tell our results, and then I'm going to give a physical argument first why what I'm going to say is basically can probably understand physically, and then I'm going to demonstrate with few models and give a general mathematical explanation for this kind of systems, basically. And then finally I'll summarize. So of course, all of you know that non-equilibrium systems produce entropy, non-equilibrium processes. And a typical example of this kind of entropy production is, for example, if you have a thermal conductor connected to two heat baths, one is at a higher temperature and one is at a lower pressure. So then heat flows from the hot reservoir to the cold reservoir. And if Q amount of heat you take out for the hot reservoir to the cold reservoir, in that case, this is the entropy change in the hot reservoir because you take out a Q amount of heat from there. And this is the entropy change in the cold reservoir, and which you immediately see that this is a positive quantity because dH is greater than Tc. Okay. So now, if you go to microscopic systems, for example, you replace this macroscopic conductor by a nanowire or something like that. Okay. So again, on the average here, heat flows from the hot reservoir to the cold reservoir, but there are fluctuations. Okay, this is not a delta function now. And this fluctuation, there can be large fluctuation in the sense that heat can also flow from the cold reservoir to the hot reservoir once in a while. So therefore, there is a distribution now associated with this quantity. So this, of course, the precise distribution will depend on the system you are looking at, but this will be some kind of typical distribution where there's some typical value, and then there will be fluctuations. Okay, and these large fluctuations are typically non-Gaussian in general. Okay, and there are also negative fluctuations which correspond to this, let's say, heat flowing in the wrong direction, cold reservoir to hot reservoir. So by now we know that all these fluctuations, heat, entropy, etc., can be defined in stochastic trajectories. So this has almost become like a textbook material now. So for example, if you have a Brownian particle in a thermal bath, so you can define what is the heat injected from the bath to the particle. So similarly, you can define entropy, which is change in the medium. And as Udo Seifert taught us, you can also define an entropy for the system, where this P is basically the probability for the state of the system. And if you consider U along any stochastic trajectories, so this also becomes a stochastic quantity. And then combining both, you can define a total entropy, and which is given by this. And if you are in the steady state, for example, then this initial and this at time t, this probability distribution, they are the same functions, and this is this P steady state. And in this case, what you find is that your probabilities of this entropy production, it satisfy a relation like that, and which is known as the fluctuation theorem. And this relation was obtained at various stages by various people, and here are a few of them, I mean, who contributed developing this theorem. Okay. So with this, okay. So now, so I'm going to go to the my talk, so which is basically the fluctuation theorem of entropy production when you don't consider a full system, but a part of the system. So what I mean by this is that suppose you have this system A and system B. So this need not be one Brownian particle, but it can be some extended system, consisting of many degrees of freedom. And then there's some coupling between system A and B. Okay. So suppose you now consider the full system A and B, this composite system, and then compute your entropy production. Of course, it's going to satisfy the fluctuation theorem. Okay. On the other hand, suppose you consider part of it. For example, you only consider system A and forget system B, but which is still coupled to system A, and there's no reason to expect that this entropy production will satisfy fluctuation theorem. So on the other hand, if you cut this coupling, so put delta equal to 0, then you know that these are like isolated system now. So therefore, if you look at the entropy production for system A, it's going to satisfy fluctuation theorem. So the question we want to pose is that, is there a deviation from fluctuation theorem? So if you take this delta, which is not equal to 0, but you take delta tending to 0 limit. So you put a very weak coupling between system A and B, and then do you expect the fluctuation theorem to be satisfied? So in fact, this question was posed earlier, for example, so in this case, so it was looked at there are these two particles, is magnetically coupled, these two particles, and then you look at the entropy production for one of these particles. And what fluctuation theorem says is that this relation with alpha equal to 1, that is a fluctuation theorem, and what these authors found out that this is not alpha equal to 1, but alpha equal to something else. Okay. But as you see that this gamma, which is the coupling, as you reduce the coupling, basically this alpha, which approaches 1. So if you reduce the coupling, which is the interaction between these two systems, in the limit gamma going to 0, it satisfies this fluctuation theorem. There are also many earlier results, so which basically looked at this effect of if you have a system and it's coupled to some other degrees of freedom, and then so if you don't consider those degrees of freedom, then what happened to the fluctuation theorem for this system? And in all these systems, what you find is that in the limit when you take coupling strength going to 0, so in this case delta going to 0, so that goes to the delta equal to 0 case. Okay? So in the limit delta going to 0, it satisfies this fluctuation theorem. So therefore, this coupling strength delta going to 0 limit is a regular perturbation around delta equal to 0. So in contrast to these studies, so what we find is that in certain situations, so there can be significant violation of fluctuation theorem even in the limit delta going to 0. So what it means is that basically delta equal to 0 and delta going to 0, these are two different limits. So therefore, delta going to 0 is a singular perturbation limit. It's not a regular perturbation around delta equal to 0. Okay. So I'm going to also tell you a general mathematical mechanism or reason why this fluctuation theorem of partial entropy production can be broken under this delta going to 0 limit, which is we call it weak coupling. Okay. So as you see that I put this weak coupling in the quote unquote, so the reason will soon become clear. So these are the references. So these are some work basically I have done with my former student Deepak Gupta, so who is now a postdoc in Simon Fraser University. Okay. So before starting, let me just give a physical argument why we expect this even in this delta going to 0 limit fluctuation theorem to be violated. So imagine that you have a Brownian particle, two Brownian particle connected by a very long polymer. Okay, and then so if these particles are close by, this polymer is very loose, and so then this fluctuation of particle B doesn't affect the fluctuation of particle A. So these two particles are basically like a weakly coupled particle. So in this case, if you consider the fluctuation of the entropy production for this system A, particle A, so what you will find is that it's going to satisfy the fluctuation theorem. But now if you let the system evolve, So what will happen is that these two particles, distance between these particles will grow, and so they typically grow like square root of t, and at some point this polymer will become a bit extended. So therefore this restoring force between these two particles, so although whatever the coupling constant is weak, the distance is long, so the restoring force becomes strong. So therefore this system which you have started with this weak coupling, over time it can go to a phase where the coupling between these two subsystems are very strong. Coupling or whatever restoring force or the coupling energy becomes very strong. Okay. So therefore, if you look at the entropy production at a time scale which is larger than this crossover time at which it goes from this weak coupling to this strong coupling regime, so then what you expect is that it should violate this fluctuation theorem. Okay. So let me demonstrate with a few examples. So first one is, this is a two Brownian particle connected by a harmonic spring. So you can think of it like this dumbbell model of polymer. Basically, it's like a minimal model of polymer. And so these two are in some temperature bath, and this delta is basically the dimensionless coupling constant. And there is a coupling, between these because of this harmonic spring, but this spring constant is very weak. Okay. And now what we are going to consider is the system A, and then we look at the entropy production for system A. So we need to keep the system also out of equilibrium, and for that what we do is that we use basically two stochastic forces on particle A and particle B, and there can be two models of stochastic forces. I mean, like we use two models of stochastic forces. In one case, we assume that this f of A is always a Gaussian white noise, and then f of B, either we assume that it's an independent Gaussian white noise, or it is something just related to A, basically, so proportional to A. So you have basically this parameter alpha, which basically says the ratio between the strength of the external force between A and B, and this theta, which basically says the strength of the external force with respect to the thermal water noise. Okay. So now we can define entropy production for this partial system, which is A, and you can define at least two ways of this partial entropy production. In the first way, we assume that, okay, we know that this system B exists, but we don't consider the system B while writing down the entropy production. So therefore, the system part, we just use the marginal for the system A. On the other hand, there can be a situation that you are not aware that there is another system coupled to your system. So this is what we call it entropy, apparent entropy production. So in this case, basically what we are going to model this system A is by this, because you are not aware that it's going to couple to something else. Although the system is evolving by these equations I wrote down before, but this is the model you are going to write down while writing down this definition of entropy production. So in this case, basically this P, which is basically the probability distribution corresponding to this Lange equation. And this one, again, so this one you can again using this, you can basically put it in a different form, basically. So we are going to use these two definitions and two choices of this force. So this first one is basically the first definition of the entropy production, and second one is the second definition of the entropy production. And this way is the first choice of the force, and this is the second choice of the force. And what you see is that in this alpha theta plane, in this 14, so except for this P1 region, which is this yellow region, in all other regions, the fluctuation theorem is violated. And this region, somehow, this yellow region, this picture, the mental picture that you this particle, and then it goes to this strong coupling limit, so that doesn't work in this regime. And in all the other cases, this entropy production violates the fluctuation theorem. You can also actually compute for the system the probability distribution basically from the theory, and you compare with simulation. And these are each basically one of the probability representative probability distribution in the one of these regimes there. And similarly, you can also compute the large deviation function from the theory. And you see that, so you can compute the large deviation function in the limit delta going to 0. Also, you can compute for different delta. And as you plot, you see that as you reduce delta, basically approaches this delta going to 0 limit. And now you see that if you take that large deviation function in the delta going to 0 limit and compute this object, so which is basically the difference between these two large deviation function, then you see that except these two regimes, so these two regimes where this difference is linear, so that means that it satisfies the fluctuation theorem. In all regimes, it violates the fluctuation theorem, even in the limit delta going to 0. This is, I am showing the same way in a different way. So you can also actually compute this asymptotic slope analytically. And what I am showing is that, okay, this analytical plot, it agrees with this analytical asymptotic, and these other lines are basically you numerically integrate and find out the large division function, and you see that it agrees with this asymptotic function. Okay. So now this system, so if you put it in a harmonic trap, so then in all regimes, of course, it now satisfies the fluctuation theorem, and that's something you can understand because this trap basically what it does is that it doesn't allow the particle to go far away, so it always stays in this weak coupling regime. So in another way of saying is that there is a time scale which is set by this trap, time scale of relaxation for the system, and then there is a time scale which is this coupling modifies the time scale, and this coupling modifies the time scale by a small amount. So it's like a regular perturbation, and you see here is that basically it satisfies this fluctuation theorem in this case. So there's another example. So where this is a it's a very minimal model of heat transport. So you have a Brownian particle which is connected to two heat baths. So if you just concentrate on the green portion, and so these two baths are at different temperature, and this is a model considered by Visco quite some time back. So, and you want to find out the entropy production for this green part. So now, in addition to this green part, so this is the Landsberg equation correspond to this green part. But in addition to this green part, what we have, so we have another Brownian particle which is weakly coupled to this other particle A. So where this delta is the dimensionless coupling strength, and even here, so when you compute the entropy production for this green part, so what you find is that it basically violates the fluctuation theorem. So fluctuation theorem would have been, this is just a straight line. Okay, so this is basically for this is a comparison of different delta with the delta going to 0 limit with this asymptotic, and it's the same plot with a one values of delta, and then compare it with a simulation. And this third one basically shows that the probability distribution function comparison with the simulation. So what you see is that basically in this case, again, it violates the fluctuation theorem, even in the limit this delta going to 0. So on the other hand, if you weakly couple to a fast degrees of freedom, as opposed to coupling to this another Brownian particle, suppose you weakly couple to a heat bath. So weakly coupling in the sense either you can basically thinking of reducing the friction and the temperature proportionately. Okay. So in this case, again, if you consider the entropy production of this green part, then in the limit delta going to 0, it satisfies the fluctuation theorem. So what it says is that basically, again, so if you couple weakly to a fast degrees of freedom, it satisfies fluctuation theorem that probably, I mean, you anyway expect. Okay. So the take-home message is that basically this picture, you should keep it in mind that So you might have a system which is a very weakly coupling, in the sense that it might have a very weak coupling constant. But if you let the system evolve, this coupling between these two systems can grow. And then if you look at the fluctuation theorem of entropy production in the large deviation way, so because when you look at it in the large deviation way, it basically considers the time scale. You actually take the time scale to infinity. So therefore, it's basically greater than all time scales in the problem. So in that case, basically, the system can violate fluctuation theorem. Even in the limit, your coupling coefficient going to 0, because you will be already considering at a time which is larger than this coupling constant, whatever the time scale set by this coupling constant. Okay, so let me just give a general mechanism why this can happen. And general mechanism, of course, restricted to this kind of system what I have described. So general mathematical mechanism in some sense. So you have this total entropy, and you want to find out the distribution of this total entropy. So instead of finding the distribution directly, what you can compute, you can also find out the generating function. And as you know that this generating function usually have this form, exponential of times some cumulant generating function. And if you consider this time average entropy production rate, which is just the total entropy divided by the amount of time you have taken to measure it. Okay, so then this distribution of this quantity you can find out from this mu of lambda by this integral, and by just doing a saddle point approximation of this integral. So which gives you this large deviation form, and where this large deviation function is related to this mu lambda by this relation, where this lambda star is just a saddle point. Now, if you have an isolated system where delta equal to 0, so you know that fluctuation theorem is satisfied. So this is given. So in this case, the large deviation form of the probability distribution will tell you that this large deviation function should satisfy this symmetry. So this is basically like a large deviation definition of fluctuation theorem, you can think of it. This also says that this mu lambda, so this subscript 0 corresponds to the delta equal to 0. So mu lambda also should satisfy a symmetry. And similarly, this lambda star, which is the saddle point, it also should satisfy some kind of symmetry. Okay, so this one is equivalent. So these are equivalent statements basically. So now, imagine that you have a case, which is our case, your mu lambda is analytic only in a given region. And outside these are just branch cut. So there are two branch points, and then inside this mu of lambda is analytic. Okay, so suppose this mu of lambda is given, it goes something like that as lambda approaches one of the branch point. So alpha 0 is something non-integer. Okay, so then you know that your set. So this is your original contour of integration, and you are going to find out the saddle point, and saddle point is going to lie somewhere here between lambda minus and lambda plus, and then you are going to detour the contour to this lambda star, and then find out the large deviation function there. Okay, so now, so as for larges, either it goes to plus infinity or minus infinity, what happens is that your saddle point either goes to lambda minus or lambda plus. So therefore, it's given by this, either it goes to lambda minus lambda plus 1 over s corrections, 1 over s to the power something correction. So therefore, your large deviation function in this two limit for large s is given by this plus this one plus your correcting term. So therefore, if you want to look at the large deviation form of the fluctuation theorem, which is this thing, which says that these two should cancel because of the symmetry you had, Galopetti coherent symmetry you had, and then there's a linear term and there is subleading term. And in this case, since you know this, there is no subleading term, so this subleading term must vanish term by term, and also this has to be equal to 1 in this case. So this is the case where you're considering an entropy production of a full system, which is the case where delta equal to 0. Now, you go to the case where you have a non-zero delta. So there is a weak coupling. So it's small, but it's still non-zero. So in this case also, so now you have these two saddle points. Now these saddle points, there need not be any symmetry between these two saddle points in this case. And unlike this delta equal to 0 case. But nevertheless, you can write down your large deviation function for large s, either going to plus infinity or minus infinity. You can, it's basically going to be an expansion around this saddle point. If s is plus infinity, it's an expansion around that. And if s is minus infinity, it's an expansion around that. So you can write down this, and then you have plus higher order terms. Okay, so this is, or this is subleading terms. So now, therefore, if you look at this difference, so there is this term plus the linear term, and then this other subleading terms. So now in this case, what happened is that this term need not be 0, which was 0 in the delta equal to 0 case because of the Galois coherent symmetry. And again, this need not be equal to 1, which was 1 in the case of this earlier one because of this Galois coherent symmetry. Okay, so therefore what you can have is that, so this is the case delta equal to 0 case. So delta equal to 0 case, you know that this is equal to s, so it is just a straight line. So now for non-zero delta, what you have is that you have something else. Okay, and you know this. So this one, of course, will be different from different thing. You don't know this region, but it will deviate from this line. But you know these two slopes, and these two slopes are just given by this. So you know this slope. So now the question in this picture, the same question, this delta going to 0, is basically that what happened to delta going to 0 limit. Whether this line, red line, it goes to this dashed line. So this red curve basically collapses to the black straight line, or it becomes something else. So if it becomes something else, then it violates fluctuation theorem. On the other hand, if it goes to the this straight line, then it satisfies this fluctuation theorem. So of course, without doing any calculation, you can see that there can be 4 possibilities. Okay, it's a different question whether these possibilities can be realized or not. So one possibility is that this delta going to 0, it basically goes back to the same 2 branch points which you found it in the delta equal to 0 case. Or what can happen is that either one of the branch point goes to the original branch point, and another, you have a new branch point, or there are 2 different branch points in the limit delta going to 0. And as you see that in these cases, all these 3 cases, your fluctuation theorem is going to be violated, except this one. In this case, because it goes with the same branch point, your fluctuation theorem is going to be satisfied. So let's see how it can happen. And so let's look at this case second. Okay, in this case, so you have just one different branch point, the other branch point is the same. So you have this one. So this, it goes back to the same branch point, and this is the branch point correspond to delta equal to 0, and this is your new branch point. So how can it happen? So if it happens, so what must happen is that your mu lambda must have an analytical part at this point, and there is a singular part. And this analytical part must go to mu 0 of lambda when you take this limit delta going to 0, because you know that mu 0 lambda is analytic here. Only branch point is here for mu 0 of lambda. So therefore, this analytic part is just mu 0 of lambda in this case. Now, the singular part, you know that if delta is exactly equal to 0, then there is no another branch point. So therefore, the singular part must vanish when you take delta equal to 0. So therefore, it must have something like that. So delta to the power some power it can be delta or some, I don't know what delta to be something, times some kind of branch point. Okay, so this alpha is okay, something again non-integer. So now if you have a cumulant generating function of this, interlimit delta going to 0, and then you find a saddle point solution from this one. So basically this is a saddle point equation you are going to solve. So what you have is that this is your saddle point equation. So this lambda tilde, just read this lambda minus tilde, because in this case. So what happens is that if the saddle point is far away from this lambda minus tilde, so in this case, you can neglect this term, right? Because you are going to take this delta going to 0 limit. So if this is large, you can neglect it. So therefore, you are going to equate this to this, and this is the saddle point equation for the delta equal to 0 case. So in this case, what you have is this, your I of s is just I0 of s. Okay. So on the other hand, as you change s, at some point, your saddle point will move closer to this lambda tilde. And in this case, at some point, this will become smaller than the numerator. Okay. Because for the delta equal to 0 case, it has to cross this lambda minus. So if from here, you can just solve the delta equal to 0 case. At some point, this saddle point is going to hit here. So in that case, so you can no longer actually ignore this, and this becomes the dominant term. You can actually forget about this one, and you are going to solve this equation. Okay. So when you solve this equation, what you find is basically that your lambda star is basically given by this one. So this is lambda star is lambda minus plus some correction term. Okay. So in this case, basically your large division function is just given by this one. Okay. So therefore, as for large s, you have a large division, different large division function, but when s is very small, your large division function coincides with the large division function of the delta equal to 0 case. Okay. So that's why you get this fluctuation theorem violation even in the limit delta going to 0. So you can either call it a violation of fluctuation theorem, or you can also call it a new kind of fluctuation theorem, which basically, instead of saying f of equal to s, its f of s is given by something else, which asymptotic forms are basically slopes are just given by this one. Okay. And these examples, what I showed before, what I showed you is that all these regimes, basically you can access in these examples. So let me just summarize. So what I have shown you is that there's a mechanism by which fluctuation theorem of entropy production can be violated in the presence of coupling to external system, even in the limit when you take coupling coefficient going to 0. Okay, this either you can call it violated, or you can call it a new fluctuation theorem, but it's just a term. And once you so this also says that in certain kind of systems, actually you can find whether your system is connected to some external system. So suppose you are interested in some kind of system, let's say Brownian system, and you want to find out whether your system is coupled to something else which you don't know. And this is one way of finding out. Suppose you apply this random force to this particle, and you apply to the random force to this particle till a time scale which, till which you are interested in doing measurements. And if you find that, okay, till this time scale, your fluctuation theorem is not violated, then probably your system is not coupled to anything else outside this. On the other hand, if it is violated, then you know that your system is coupled to something else. Okay, so this also demonstrates it's possible to basically observe effect of weak coupling if you go look at a time scale which is set beyond this time scale set by this weak coupling. And of course, it doesn't explain everything. Like even there, I showed you that there's these two yellow regimes where this simple picture that, okay, you have this thing, and then at some point, this two particles becomes very strongly coupled. So somehow in some regimes, it doesn't seem to work, this simple picture, yeah. Yeah, okay. Thank you for your attention. And if there are any more questions, if there is any question, I'll be able to.
So, so now we go to the question part. Okay, but perhaps I can try one myself. I mean, this structure where you have these two slope, which are different from the slope that you get when the FT is verified. I wonder if you can work out the difference in the slopes, because I mean, I remember some time ago we looked at something like that, and there was then the new slope was related to the effective temperature. For instance, when there is an effective temperature, it would show up in the new slope when the FT is not obeyed. So I wonder if you looked at the slope in this case, the new slope, if you see what I mean.
Yeah. So yeah, I think these examples basically finally yeah, it is related to some kind of effective temperature in terms of this alpha and theta, basically.
Okay.
In these examples, yes. Yeah.
Yes, there's one. Isaac, you can go.
Yes. It's just a probably basic question, but when you say weak coupling regime and strong coupling regime, what do you exactly mean by strong coupling regime? Is that a way? Can you quantify that? Or?
Yeah. So what I meant is that suppose you have a spring constant K, which is very small. Now, if suppose it's a harmonic system, so it will appear like minus kx in the Landsberg equation, right? So now if x is very small or order 1, so then this force is very small. So it basically doesn't affect your Landsberg equation. So that's like a very weak coupling. But now if the separation grows between these two particles, the separation when becomes of order, let's say 1 over the coupling, so then you cannot neglect this term because that term now becomes of order 1. These are comparable to all the other terms. And that's the regime where basically you call it's a strong coupling regime.
Okay, I see. Yes. Yeah, that makes sense. Thanks.
Yes. Yeah. So that's the time scale basically when these two particles which goes to equilibrium between themselves basically. And that time scale is quite long, and that's the time scale basically. So now if you look at the entropy production in that time scale, then what you will see is that violates the fluctuation theorem.
Okay, so it looks there's no more urgent questions. So I guess we can close it for this morning session.